This video is in Geometry section 7.4. We're going to talk about special right triangles, their relationship. If you can learn those relationships, memorize them, or have them in your notes, it will be really helpful. In this section, we're going to talk about two types of right triangles that we see fairly often, especially in construction or all kinds of applications. And we're going to look at the relationships between the sides in those special triangles and see if we can memorize them so that we're not having to do the Pythagorean theorem every single time or with every single problem. Let's start with this one. This is the 45, 45, 90 right triangle. These two angles are the same, which means the sides, those are like the base angles. If the two angles are the same, then the sides across from them are the same. So this always will be an isosceles right triangle. Because these 45s are the same, these sides will be the same. Let's just say, I don't know what the length of that side is, but let's just say it's x. Okay, so I'll just call it x. That means this leg is also x. My legs are both the same because it's isosceles. If I do the Pythagorean theorem, then x squared plus x squared will equal my hypotenuse squared. Let me show you what that would look like. So I put an h for the hypotenuse. X squared plus x squared will equal the hypotenuse squared. Since these are like terms, I can combine them. I have 2x squareds. 2x squareds will equal the hypotenuse squared. Now, to solve for the hypotenuse, I need to take the square root of both sides. So the square root of hypotenuse squared is just that hypotenuse. The square root of 2x squared. Square root of 2 I can't pull out, but what's the square root of x squared? It's just x. So whatever this number is, it's going to come out. This simplifies to be x square root of 2. So our hypotenuse is always x square root of 2. It doesn't matter what x is. These legs can be any length. This relationship will always be the same. This means that in any 45, 45, 90 triangle, you really only need one side in order to find the other three. Because you know the two legs will always be the same, and the hypotenuse will always be the length of the leg, whatever it is, times the square root of 2. And you've got it. Let's say all I know is one leg, and it happens to be 3. Then what's the rest of the triangle? Well, it's 45, 45. My legs are the same. So if this is 3, this is also 3. And I have in my notes, or I have memorized, or I'm looking at the poster, big poster in Mrs. K's classroom. This hypotenuse will be the leg times the square root of 2. So it will be 3 square root of 2. And you're done. What if the information we have is kind of backwards from that? We don't know the length of the sides, but we do know that this hypotenuse is 12. How would we find the two legs? Remember that this hypotenuse equals the length times the square root of 2. I'm sorry, the leg times the square root of 2. So if this is x and it's what I'm trying to find, then that x times the square root of 2 came to be exactly 12. How do we solve for x? Just like any other equation, we're going to need to divide by the square root of 2. So my x is 12 divided by square root of 2. And you might think you're done, but we do not leave irrational numbers in the denominator of a fraction. Because remember, a fraction is a division problem, and you can't divide by an irrational number. It's impossible. So we need to get rid of that radical in the denominator. And the way we're going to do it is we're going to multiply this denominator by whatever will get rid of square root of 2. And what will do that is another square root of 2. So we're going to multiply this by the square root of 2 over the square root of 2. In essence, we're multiplying by 1, so we are not going to change the value of this at all, just the way it looks. We're just going to rationalize that denominator, which means we're going to get rid of that radical. So I have 12 square root of 2 in the numerator, and the square root of 2 times the square root of 2 is the square root of 4, which is just 2. So this is 2. And now I can reduce, because 12 divided by 2 is 6. So this becomes 6 square root of 2. So my legs are 6 square root of 2. That may have seemed complicated, but after you do it a few times, it becomes really quick and easy. So know if you're going from the leg to the hypotenuse, you multiply by the square root of 2. So you're just going to do the opposite. If you're going from the hypotenuse to the leg, you're going to divide by the square root of 2. It's that simple, really. Let's check to make sure we got it right. If my leg is 6 square root of 2, then 6 square root of 2 times the square root of 2 should equal 12, if it's right. Because remember, the length of the leg times the square root of 2 equals that hypotenuse. So the 6 square root of 2 times the square root of 2 is 6 square root of 4, and the square root of 4 is 2. That's 6 times 2, and sure enough, that's 12. Another application of this special triangle is it's actually a square divided diagonally. So if I find the diagonal of a square, I have divided a square into 2 triangles, 45, 45. 2 isosceles, 45, 45. This is the side of my square. So the diagonal of a square will be the length of the side times the square root of 2. And so any kind of word problem type application of 45, 45, 90 is just a square divided in half diagonally. Okay, to introduce the next special triangle, I want to take what is an equilateral triangle. Here's an equilateral triangle, which means all my sides are the same and all my angles are 60. And what I'm going to do is I'm going to divide this equilateral triangle in half by drawing an altitude or a perpendicular bisector right down the middle. So let me do that. Okay, here's my triangle. I've divided it in half. What that did is it bisected this angle here and made 2 30-degree angles. Now I have 2 right triangles, 30, 60, 90 triangles. This is a common triangle. Just like 45, 45, the 30, 60 is also quite common, probably because it does equally divide an equilateral triangle. I'm going to put some numbers on here, and we're going to work through the Pythagorean theorem with this one just to see if we could figure out the relationships between the sides in the 30, 60, 90. So let's pretend that each side in this equilateral triangle was 10, which means this base was also 10. But when I divided it in half, this became 5 and that became 5. Now I want to only look at 1/2 of this triangle here, and I want to figure out this height, this altitude. So I'll use the Pythagorean theorem. 5 squared plus this height squared, whatever it is, this height squared, this other leg, equals the hypotenuse, which is 10 squared. So this is 25, this is 100, this is 100, which means my height squared equals 75. I keep seeing that H and thinking hypotenuse, but in this case I meant height. All right, so this leg, my leg height is squared is 75. So let's take the square root of 75. The square root of 75. 75 is 25 times 3, isn't it? And the square root of 25 is 5. So I'm going to pull that out. It's going to become a 5, and that 3 will be left inside. So it is actually 5 times the square root of 3. And if you notice, 5 is the short leg. That's why every 30, 60, 90 triangle has the following relationship between the legs and the hypotenuse. In a 30, 60, 90, we have a short leg, we have a long leg, and we have a hypotenuse. And I wrote in parentheses the numbers that we came up with last time when we used the Pythagorean theorem. And the hypotenuse ended up being the length of that equilateral triangle, that was 10. Then when we cut this in half, it was half of that, which was 5. And then this longer leg was 5 square root of 3. Those relationships are constant. If I call my short leg x, no matter what it is, my hypotenuse will be twice that. I just doubled the short leg. So this hypotenuse is 2 times that, and my long leg is the short leg times the square root of 3. Those relationships are constant. So remember, a square used the square root of 2. The 30, 60 uses the square root of 3. 30 and 60 both can be divided by 3. That's how you can keep them straight. This one, square root of 3. Let's try a few problems with this. Let's say I have a 30, 60, 90, and all I am given is the short leg, and I need to find the other sides. So look at your notes, or look at my poster on the board, or just memorize, even better, the relationships between the sides. If the short leg is 7, the long leg is the short leg times the square root of 3, and the hypotenuse is the short leg times 2. And there you go. Let's say I'm given the hypotenuse and I need to find the 2 legs. Remember that the hypotenuse is twice the length of the short leg. So this is 17 over 2 or 8.5. Either way, 17 over 2 or 8.5, same. And then the long leg is the short leg times the square root of 3. And you have it. Let's say all they give us is the long leg. In this case, the long leg is 12, and now we have to find the other 2. Definitely find the short leg first. So remember that the short leg times the square root of 3 came out to be 12. So what we're going to do then to solve for that short leg is divide by the square root of 3. Remember, we are going to rationalize the denominator. We're not going to leave that square root of 3 down there. So I'm going to multiply by the square root of 3 over the square root of 3. And this becomes 12 square root of 3 over 3. I can reduce 12 over 3 to 4. So my short leg is 4 square root of 3. I can double check. 4 square root of 3 times the square root of 3 does equal 12. Now, how do I get from there to the hypotenuse? Remember, I take the short leg and I multiply it by 2. You don't multiply this radical. The radical just hangs on just like a variable does. You could treat it just as if it was an x. So if I want to multiply that by 2, it becomes 8 square roots of 3. Here I have 4 square roots of 3. Here, double that. Now I have 8 square root of 3. And those are my 3 sides. If you are asked what that is to the nearest 10th or the nearest 100th or whatever, you would put that in your calculator and you would say, oh, that's about whatever it is. And I'm not going to bother to do that right now, but that's what you would do. I'm going to walk you through a new formula for finding the area of an equilateral triangle if all you have are the sides. All the sides are the same. So you know what the side lengths are of this equilateral triangle. You want to find the area. And remember, the area of a triangle is 1/2 base times height. So that base would be the same as the length of the side. You would just need to find that height and then multiply all of that together. So remember, if you are looking for this, you need to find the height. So the height is the short leg here, which happens to be 1/2 the base, times the square root of 3. That's your height. So 1/2 of that side length, 1/2 of that side length times the square root of 3 is equal to your height. Right? I know the side, half of that side times the square root of 3 equals my height. My base is just the side length. So what we have is 1/2 times one side, which is the base, times 1/2 of that side times the square root of 3. And now, well, this is supposed to be 1/2. Sorry about that. Now we're going to simplify this. 1/2 times 1/2 is 1/4. Side times side is side squared, square root of 3. Or you can just say the side squared, square root of 3 divided by 4 will give you the area. Your book lists the formula as the square root of 3 over 4 times the side squared. That also works. Doesn't matter how you arrange it, it's all the same. And if you want to put that formula, either way, in your notes and use that, by all means do. To me, it's so much easier just to realize that the area is 1/2 of the base times the height. So whatever the side length is, you can just divide that in half, and it's that times that square root of 3, and you've got it. Anyway, use whatever method you want, but here's a nice little formula for helping you. I have a triangular prism here, and I want to know the area of the two ends of my packaging. I know they're equilateral triangles with a side length of 5. How can I use that formula to find it? So we take that side, square root of 3 over 4 times that side squared, which is 25. So it's 25 square root of 3 over 4, and we put that in our calculator. This represents the exact area. This is the approximate area. Okay, let's practice a few problems. I have a 45, 45, 90 triangle here. What is the length of the hypotenuse? Hopefully you said it's 4 square root of 2. If you did, good job. Same triangle. Now one of the legs measures 2 square root of 2. Now what's the length of the hypotenuse? This might have been trickier for you, I don't know, but 2 square root of 2 times the square root of 2 is actually 4. Here's a 30, 60, 90 triangle. The short leg has a length of 3. Find the other two. Okay, hopefully you paused it if you needed to and you figured it out. If the short leg is 3, the long leg is 3 square root of 3, and the hypotenuse is 3 times 2, or 6. Same triangle, only now the longer leg has a length of 3. What's the length of the shorter leg and the hypotenuse? This one's trickier. Pause the video if you need to, and then I'll walk through this one. You multiply the short leg times the square root of 3 to get this length. So to go backwards, we're going to take this length and divide it by the square root of 3 to get the short leg. Remember, we are going to rationalize the denominator. We end up with 3 square root of 3 over 3. These two cross cancel. The shorter leg is square root of 3. How do we get from there to the hypotenuse? We double that. If that's 1 square root of 3, to double that, I have 2 square root of 3. And those are the dimensions of the other two sides. One more. Now the hypotenuse is 2 square root of 6. Can I find the 2 legs? Try that. Okay, hopefully you paused the video and actually worked through it. Remember that this hypotenuse is the shorter leg doubled times 2. So to undo that, we're going to divide it by 2. 2 square root of 6 divided by 2 is square root of 6. That's the shorter leg. The longer leg is the shorter leg times the square root of 3. So now we have the square root of 6 times the square root of 3. That is the square root of 18. And 18 is 9 times 2. 9 is a perfect square factor. So we're going to take that out and it's going to become a 3 and our 2 will be left inside. And look at that. All 3 sides are radicals. They're all 3 square roots. Okay, I hope this was helpful to you as you're trying to work now with these special triangles. It is worth memorizing or at least keeping handy the 2 arrangements, the special 45, 45, 90 and the 30, 60, 90. Pythagorean theorem will always work, but if you can remember these, you have to have 2 sides for a Pythagorean theorem. With these, you will only need 1. So that is it for section 7.4. Hopefully this was helpful.